Next, I'm going to illustrate some basic correlations. So here is a correlation matrix computed by first creating a data frame by c-binding some of these variable names, which remember are already in a data frame, but I am referring to them by name because that data frame is attached, and I'm putting them in a new smaller data frame temporarily in order to call the core function. Use equals pair is necessary because the core function will give a missing value for the correlation if any of the values are missing, unless you specify what to do with missing values. So here I'm going to use all of the cases that have complete data on each pair of observations, which means that this is not in a strict traditional sense a true correlation matrix. At least it's not based on the same data for all the correlations, but close to it. So here's a matrix of those correlations. It wrapped onto a second row. That's fine. If I wanted to spend some time talking about these, I could. So trust in the courts is not very highly correlated with the perception that most people support discrimination, for example. But the view that discrimination is legal is correlated with believing that most people support discrimination and with personally supporting discrimination. So in this core function, I did use equals pair. Here I have a note. If I wanted, I could say use equals complete. If I wanted a correlation matrix with all of the missing values excluded listwise. Those are both abbreviations. The values the argument takes are complete obs and pairwise complete obs, among other things. But abbreviations are acceptable for this particular function, so I just tend to use pair and complete because I find those to be intuitive ways to describe those arguments. And this also goes for variable names. This like abbreviating thing works. It doesn't work in every case for every kind of function, but it does actually work for variable names in data frames. So we have this discrim is legal variable in data.ok, and I can refer to it here. I can also refer to data.ok $disc and get the same variable. That's because the only variable name in data.ok that begins with disc is discrim is legal. Also, let's say I wanted to look at the correlation between most people support discrimination and I support discrimination, and I don't just want the correlation that I saw in this correlation matrix above, which is 0.53, but I want the t-test of whether that correlation is significantly different from 0 under the normality assumption. That's what this core.test function is designed for. So I supplied two arguments. Both are names of vectors, which are actually columns in a data frame, and R calculates the t-test for me. This is the traditional correlation test that you're probably quite familiar with. So the correlation is 0.53, and the p-value is very, very small, which should not come as a surprise because the correlation is 0.53. Another thing that might be helpful for looking at bivariate relationships is a scatter plot, which is by default what the plot function does if you supply two numeric vectors as arguments. So here's that scatter plot of these two variables together. And one last thing I'm going to show you is the pairs function, which can take a data frame as its argument. So here I'm creating a small data frame out of these same 6 variables that I've been looking at so far. You could plug in your entire data set, but it would be the result would be an unreadable plot. This pairs function just shows you plots of all of the variables against each other. So I'm going to try and make this visible. The names of the variables are kind of on the diagonal of this matrix here, and these are all scatter plots between each pair of them. So the scatter plot that is in the second row, first column, is a scatter plot with discrim is legal on the horizontal axis and most support discrim on the vertical axis, because those labels appear closest to those axes on the diagonal, and that's how you read this kind of pair plot. So Some things that I can notice here is that discrim is legal, first of all, has these, appears to be more discrete than the rest of these variables. It has these, a relatively small number of unique values. I know this makes sense because it's the composite of just two Likert scales, and so it can only have values that are a multiple of zero 0.5, whereas the rest of these are averages of many more items together. I'm also noticing that Amy eval and standardized eval are highly correlated. That's like the strongest appearing correlation in this set of scatter plots. That also should not come as a surprise because Amy disclosed having a history of depression. So she's an example of a member of the group that they're evaluating for that other question. This kind of plot is a bit gimmicky. I would never put it in a paper, but I use it from time to time if I need a very quick glance at some data, and I don't need it to look pretty. So there's still some more of this example analysis, and I think it might be reasonable to continue going over it next week. So I'll keep track of where we are. Next week, the plan is to talk about my example, more sophisticated example plots that I posted on my website. But I'll just finish up going over this example analysis first and do that next week.